Hello everyone, this is part 2 of RC and Rlc Circuits. Last time we went through the theory. This is the first page of the notes behind RLC circuits in general. So we got to the two main equations that are at the bottom there, and then I reminded you of the fact that if we're going to solve an RC circuit, L is 0, and so it's actually a first order non-homogeneous differential equation, and we'll have to use the integrating factor. So here we gave an example of using the integrating factor with x's and y's, but then we talked about, and this is where we left off last time, the fact that the equation that we're going to start with here is analogous to the equation for the integrating factor. So we're going to, as a summary mentions here, we're going to start with this equation for the RC circuit, replace R, C, and E of t, and use the integrating factor to find the charge, and then to find the current, we'll just take the derivative of the charge. So let's see a couple examples. Okay, so I'm going to find the charge and the current. First, for the charge, okay, we always start with just our basic equation. This is on your cheat sheet for the exam. R dq dt plus 1 over c times q is equal to E of t. You can see everything's given. It's basically just an initial value problem. So we substitute R is 10, dq dt stays, so q is the variable now. Q is the dependent, time is independent. 1 over c, so that's 1 over, you may want to actually rewrite c as 0.0004, because it's 10 to the negative fourth. So let's do it that way. 1 over 0.0004 times q again is the variable, and E of t in this case is just a constant, it's 50 volts. So let's just take our time here. 1 over 0.0004 is 2,500. Q equaling 50. Let me just double check that. I don't want to have a virtual pizza party or anything. Yep. Okay, so then we'll divide everything by 10, because we're going to have to use the integrating factor. So we have to isolate, in this case, the dq dt. So dq dt plus 250q is equal to 5. So note that that's a non-homogeneous first order linear differential equation. All of them are linear, as we've mentioned, that we're going to study. But that's where we need the integrating factor. So the integrating factor rho is e to the integral of, this would be p of t, the coefficient of q, which is 250 with respect to t. And so that gives us e to the 250t. So then we multiply. So we're multiplying everything by e to the 250t. So e to the 250t times dq dt plus 250. I'll slide the e to the 250t in there times q is equal to 5, and don't forget to multiply the right-hand side by the integrating factor as well. So 5e to the 250t. So then the left-hand side is expressible as the derivative of a product, and that product in particular is the product of, in this case, the variable q and the integrating factor. But remember, one way to think of it is, if you look at after multiplying by the integrating factor, if you look at the left-hand side and you focus on the term containing the derivative, just take away its derivativeness. So what I mean by that is e to the 250t times just q is going to be the product that gives us that left-hand side. And you could verify that, as I always encourage you to do so. Excuse me, here's the first factor, e to the 250t, derivative of the second, dq dt, plus the second factor q, and derivative of the first, and the derivative of e to the 250t is e to the 250t times 250. So then that's equal to the right-hand side. Okay, so now we can integrate. So if you want to rewrite it, you can. I'm just going to jump in here with the red colored pen, indicate I'm integrating both sides. You don't need a dt over here because that's a differential. You formally should include a dt over here, or just don't even show it and jump right to the integration. And the integral of the derivative of something is that something. So e to the 250t times q is equal to, okay, here we have to use our rule for integrating e to the kt, which is 1 over k, so the 5 tags along, and they get 1 over 250, e to the 250t, and we get our constant of integration. So let me just do this. I'm just going to rewrite it. 5 over 250, 0.02 is a decimal. Okay, and then we're going to solve for q. So divide everything by e to the 250t. And so we get that q of t is equal to 0.02, because the e to the 250t's cancel, and then plus c, let's swing that e up to the numerator as e to the negative 250t. And now we need the initial conditions to solve for c. And the initial conditions are that q of 0 is 0.015, so that was from the given up here. 0.015 is q of 0. And so then that means that q is 0.015, equaling 0.02 plus c, because t is 0. And so c is, subtracting 0.02 from both sides, we get negative 0.005. So then that gives us our function, our charge as a function of time. Just substitute back in the negative 0.005 for c. So 0.02 minus 0.005 e to the negative 250t. Okay, so that's our charge, and then for our current, I of t is, well, you can think of it in one of two ways, dq dt, differential notation, or q prime of t in terms of just our prime notation. So therefore, I of t is q prime of t, which is, okay, the derivative of 0.02 is 0, the negative 0.005 tags along, and now keep in mind this is differentiation here, so the derivative of e to the u is e to the u, so e to the negative 250t, then don't forget times the derivative of the power on the base of e, so times negative 250, so finally we get I of t is negative 250 times the negative 0.005, 1.25, and then we have e to the negative 250t. Okay, so we'll look at one more example. Note that this example had one more example of the RC circuit, then we're going to turn our attention to our Rlc circuits. But notice that this example, the charge E of t was a constant. Not that it's really going to make that much of a significant difference, but now we'll look at the charge being, in this case, a function of t. So we're going to start the same way. For the charge, we want the charge and the current again. And so for the charge, we're going to start with the equation R dq dt plus 1 over c times q equals e of t. And we just make our substitutions. So R was 25, so 25 dq dt plus, okay, 1 over 0.002 for c times q equals, now e is 50 e to the negative 10t. Okay, so standard form, well, first off, so we don't make any careless mistakes here, let's take 1 over 0.002 is 500 q. Okay, and now our standard form, because this again is going to be a first order non-homogeneous differential equation, and we're going to need our integrating factor. So we isolate the dq dt by dividing everything by 25. So dq dt plus 500 divided by 25 is 20. Q equaling to e to the negative 10t. Okay, so now for the integrating factor rho, it's e to the integral of p of t, the coefficient of q, in our standard form, 20 with respect to t, so e to the 20t, and then we multiply, so we get e to the 20t dq dt plus 20, I'll slide the e to the 20t in there, times q equaling, okay, make sure you multiply e to the 20t by this right hand side as well, and we get 2 e to the 10t, because we're adding exponents. So at that point, okay, so at that point, again, make sure you get e to the 10t on the right hand side there. So you're multiplying that by e to the 20t. Okay, left hand side now expressible as the derivative of the product. That product would be e to the 20t times q. And I encourage you to double check that that's true. And that's equal to 0.2 e to the 10t. Okay, at that point we'll integrate, and you could rewrite it, or just simply throw the integral symbol in front of each side, or just integrate it. But integrating the derivative of this something, we get that something, so e to the 20t times q equaling, okay, the 2 tags along, integrating e to the 10t, that's e to the kt once again, so 1 over 10 e to the 10t, then add our constant, so e to the 20t q equals 0.2 e to the 10t plus our constant. Now we'll solve for q, so divide by e to the 20t. And we have that q of t, you could just say q, but I'm going to say q of t is, okay, this would be 0.2 e to the negative 10t when we're subtracting the exponents, and then plus c, and let's bring the e to the 20t up to the numerator as e to the negative 20t. And now the initial conditions to solve for c. So the initial conditions, if you look back up at the top, is q of 0 is 0. So that means that 0 is equal to 0.2, e to the 0 is 1, so 0.2, and then plus c, because e to the 0 is 1. So then c is negative 0.2. And so then that gives us, that answers the first part of the question. Our charge as a function of time, or q of t, is now 0.2 e to the negative 10t minus 0.2 e to the negative 20t. Okay, so then we were asked for the current as well. And the current, once again, I of t, just q prime of t, or if you like dq dt. That just means take the derivative. So I of t, just take the derivative of the charge. Okay, so make sure you put yourself in the differentiation mode here. 0.2 derivative of e to the u, so just recopy, e to the negative 10t, but then don't forget, times the derivative of the power on the base of e, or the derivative of negative 10t with respect to t, which is negative 10, and then similarly we have minus 0.2 derivative of e to the negative 20t, e to the negative 20t times negative 20. Okay, so therefore I of t is, let's see, that would make this negative 2, negative 10 times 0.2 that is, e to the negative 10t, and this would make it plus 4, e to the negative 20t. Okay, so those are typical examples of RC circuits. And next thing is to discuss Rlc circuits. We're going to have to come back on another video, but I just want to show you what it's going to look like. This does need a little bit of discussion, so in the next page it's devoted entirely to Rlc circuits. So you can see we have our two main equations again, and we're going to start with, as opposed to solving for the charge in an RC circuit, then finding the current, in an RLC circuit, we're going to solve for the current, and then if necessary, we'll find the charge. So we're going to start now with this Li double prime equation. And a couple things to note, that it's homogeneous if E of t is a constant, because notice it's equal to E prime of t, and if E of t is a constant, then its derivative is just going to be 0. it's non-homogeneous if we have a function of t for e of t. And if it is non-homogeneous, then we have to consider the two parts to the solution, complementary function as well as the particular. And moreover, so this is an added dimension that's a little bit, you wouldn't expect this one coming, because we have to use the initial conditions, and we're going to be given the initial conditions. You can know the charge and the current, but if we have to use the initial conditions regarding current, we're going to need I prime of 0, and there's no way to measure that. So what we have to do is calculate it. So to find I prime of 0, first consider the equation Li double prime, etc. And recall that that came from taking the derivative of LQ double prime, because Q double prime is I prime and Q prime is I. So we replace those, and we have this equation in terms of I and Q. So it's kind of a mixed equation, but necessary, because note that we're going to know L, we're going to know R, and we're going to know C. And we will also know I and Q at t equaling 0. And we also have to calculate E of 0 as well. And so if we let t equal 0 in this equation, this is what we come up with. So after we find the general solution, we find I prime of 0 by making our substitutions, because everything else is going to be known. And then we'll have I prime of 0, and we'll be able to use that to find the particular solution in combination with Q of 0 and I prime of 0. Or just I of 0, excuse me. Okay, so we'll come back and we'll revisit this page and kind of reiterate what we just said, and then we'll see 2 more examples of solving RLC circuits, and that will end the material for the 3rd exam.